Hello again. Welcome back to grade 12 University Physics, here with Mr. Stone. So here we are in Unit 1 still in Lesson 2. We're going to talk about what we call connected objects. So we're still thinking about frames of reference and how frames of reference can help us. So we're going to use something called an Atwood machine to help us understand, using frames of reference again. So an Atwood machine is basically just two masses, attached to a pulley. So there's going to be some sort of force pulling on one in downward direction, another force on the other, and they're going to slow each other down. So these were used originally in physics experiments a long time ago because 9.81 meters a second down is actually quite fast. And given the experimental apparatuses that they had, in the 17th century, it was difficult to calculate things using these things. So, using dropping objects. So they came up with this idea of having a counterweight to slow things down, so that instead of things dropping at every second increasing speed by 10 meters a second, they had a counterweight to slow it down. Now, to analyze how an Atwood machine like this functions, it's going to be a little bit difficult because how can we come up with a way to consider distances and speeds and accelerations and that sort of thing when they're traveling in opposite directions? Right, let's say that the green block here is much heavier than the blue block, so then it's going to be the green block is going to be going down, and at the same time, the same amount of displacement in the vertical direction is going to be happening to the blue block, but in the opposite direction. So we're going to have to do something funny with you know which object is moving up, which one's down. It's going to be confusing. So we're going to change our frame of reference such that we straighten out the whole system. Now, what do I mean by that? Now, let's take the whole system and instead treat it as well, wait a sec. Okay, sorry. So let's think about forces acting on this. So mass 1, which is smaller than mass 2, this is going to be pulling down, right? And M2, again, we're going to have a force of gravity. Notice that the force of gravity vector is much larger than the the force of gravity vector on 2 is much larger than the force of gravity on 1. So we know that M2 is going to be going down and M1 is going to be going up. Now, the reason that they're not just like falling is there's a string attached to them, and that's going to provide a tension force. This is going to be up the string in both examples here, both objects. However, those tension forces will cancel. Remember that these tension forces, according to Newton's third law, are there because of the reaction force. So this string is providing a reaction force that's going to slow down M2. Right, you can think about this one, the red vector here, the FG2, is going to be larger than FT. So this is going to be accelerating downwards, whereas M1, the force of tension, is much larger than FG1, so it's going to be accelerating upwards. So again, how are we going to come up with a frame of reference to understand this in a more meaningful way? We're going to straighten out the whole system. We're going to imagine that instead of the objects going up and down or down and up, opposite each other, the whole system is going to be moving left to right or right to left, however it's set up. And that's going to make everything so much easier for us because now we won't have to worry about, as one goes up, the other one goes down. We can just go from there. So we're going to have FG1 pulling on mass 1 in the left direction now. Right, that's going to be, right, imagine our two masses. Now we're going to stretch the whole thing up. So instead of going down, it's going to be going up. And then the whole thing is going to move to the left or right, whichever way we're looking at it. And there's going to be a force of gravity on 2. And there's going to be the tension force. And now you can see that those two tension forces cancel each other out. And then as a net force, right? The net force acting on this is going to be the vector sum of Fg2 and Fg1. And notice that this will provide a net force to the right, which will provide an acceleration for the whole system to the right. And then we can convert it back to our actual lab frame of reference, and that means that as the whole system moves to the right, that means that mass 2 goes down and mass 1 goes up. But from a mathematical point of view, we can just treat this like the whole system is moving left to right, or right to left in this case. So that's one way we can look at it. Or we can then look at it in an alternative way where we take our whole system and we break it up into two pieces. So M1 has that tension force pulling to the right, the force of gravity pulling to the left, but notice that the force of tension is much larger than Fg1. So that'll provide an acceleration to the right. Similarly, Fg2 is much larger than the tension force, which will provide an acceleration to the right. And keep in mind that those two accelerations are equal, and we're going to call it just A, which is the same A that we looked at in our first viewpoint. Okay, so we're going to have to use both these viewpoints for solving different types of problems. So let's try an example here. So let's say we have an Atwood machine, just like we talked about, where the masses are 175 for mass 1 and 75 for M2. So in this case, M1 is larger than M2. So the whole thing, wait a second, so my picture is actually wrong. Give me a second here. All right, sorry about that. So let's just switch the ones and twos. Okay, so M1 is 175. It's much larger than M2, which is 75. So how do we start any problem involving dynamics? What do we do? Oh, sorry. First of all, the frame of reference in this case, we're going to decide, because we know that Fg1 is much larger than Fg2, the whole system is going to move to the right. So we're going to say that the right direction is positive. Okay, so anytime we talk about a positive acceleration, velocity, whatever, that's going to be going to the right. Okay, so F equals ma. Right away, that's where we start always. F equals ma. Force is equal to mass times acceleration. Now, what is the force acting on this thing? The forces are going to be Fg1 and Fg2. Right, the tension forces will cancel, so we don't have to worry about those. And one thing we have to be careful of is the m is going to represent the mass of the whole system. So instead of writing m, we're going to have to write m1 plus m2, because we're treating the whole system as one object. Right, we're thinking about the whole object. The two masses and the string itself is just one thing that's going to be moving to the right. So we're going to have to treat m as m1 plus m2. Then I know that the force of gravity on 1, wait a second, sorry, so the mass 1 is moving to the right, so we're gonna have that as a positive, right? Because this larger vector here, Fg1, is in the right direction, which is positive, which means we're going to end up having a positive sign for this term, right? This is going to be positive here. However, Fg2, sorry, is going to be going to the left. This smaller vector is to the left. That's the negative direction, so I have a negative sign here. I can factor out the g and divide both sides by m1 plus m2. Right, if I factor out g, since g is a common factor here, I factor out the g, and I end up with m1 minus m2. So then I have this nice term here, which is a unitless coefficient, right? Acceleration is meters per second squared. G is meters per second squared. This term here ends up being sort of my my Atwood machine. It's the thing that slows it down. What the factor by which it's slowed down. Okay, which relates to in the denominator. That's the sort of inertial term. Right, that's how much inertia there is in the system, how much it's being slowed down. And the top is sort of the difference between the two masses. right? The larger, if M1, the difference between M1 and M2 is very big, this term will be pretty large, right? And will have a large amount of acceleration. But if the difference is small, right? If the two masses are similar mass, this term will be very small, and then the whole thing will be very small, right? Let's say one's 9 and one's 10. So we'll end up with a difference of 1 over 19, right? Which is, what's that, like 5% of gravity. So let's keep going and put some numbers in here. So 175 take away 75, and that works out to about 4 meters a second squared. So it slowed it down by about 40%. Slowed it down by 60%, I guess. 40% is left of the typical acceleration due to gravity. Okay, and now I can actually put that as a vector because I know that the whole acceleration of the system is, or let's say the acceleration of, this is of M1, right? The acceleration of M2 would actually be 3.9, negative 3.9 meters per second squared down. Or easier, 3.9 meters a second squared. Oops, second squared. There's another way we could think about that. Okay? Apologies for my scribbles. All right. So the whole idea here is that the two masses act in opposite directions. They slow each other down. The whole system is itself inertially, acting, so it slows it down. So it doesn't accelerate at 9.81 meters a second, and the amount that it slowed down is this factor here. Okay. So we can then finally say, as a therefore statement, the second mass is going down at 3.9 meters a second, and the first mass is going up at 3.9 meters a second squared. Okay. All right. So next we can actually calculate the tension. How much tension is in the string? How much tension is pulling up on both masses? And in that case, we're going to have to look at it from the other perspective, where we're looking at it as two separate objects. So let's look just at mass 1. So mass 1 has two forces acting on it. There's gravity pulling down to the left, and the force of tension pulling up the string, or in this case, to the right. Remember, we've changed our frame of reference. So using our frame of reference as right positive again, the whole system will accelerate to the right. Then I can plug in my, into F equals ma, and I know that the only mass I care about now is m1. So I can say m1 times a. A is that a that we just calculated in the whole system. So that's going to be equal to the tension pulling on it plus the gravity pulling on it as well, in the opposite direction. So when I plug in my actual values, careful here, I'm going to put a negative m1g because that's going to be pulling it in the negative direction. Then solving for ft, I'm going to get, right, I'm going to bring ft, I'm going to bring this guy over that way, it becomes positive, factoring out m1, plugging in my values, and I get 570 newtons up the string, okay, which is going to be the same tension on the other mass. Right, we could have done this exact same calculation using M2, and I would have got the same number. Notice here I rounded that to two significant figures. And this 3.9, that came from our previous problem where we solved the acceleration. Right, that's what this A is. That was the A of the system that we calculated in the first half. All right, and there we go. That's how we solve these problems. All right. So these systems really, this is an example of changing a frame of reference such that it becomes simpler, right? That's the whole point of using these frames of reference. Notice also quickly, when I had a final answer for my problem here, I rounded it to 3.9. I rounded it to two significant figures. But when I plugged it into my problem here, I kept all the significant digits. Okay, we only round for our significant digits at the very end of the problem. Otherwise, you keep a couple extra, at least one, so that we have enough significant digits to not have rounding errors as we go through. All right, so let's try another one. In this case, the second mass, or M1 in this case, it won't be hanging, but it'll be sitting on a board. So in this case, gravity won't be pulling on it. It'll just be acting as an inertial damper, something that increases the mass of the whole system and slows it down. Okay, so I have a 3 kilogram mass on the board and a 5 kilogram mass hanging. What is the acceleration of each block if the board is frictionless? So again, I can take the whole system, and instead of worrying about left, right, up, down, let's straighten the whole system out. So instead, we'll look at it from a point of view of M1 here, pulling it to the right. Sorry, the tension, the string is pulling it to the right. See how this mass is going to be here? So there's going to be a string pulling this way. There's going to be gravity pulling this way. And there's going to be tension on the string, slowing down M2, so it doesn't fall at 9.81 meters a second squared. Right? And these two forces, these two tensions, are going to be the same. So I can rearrange it, again, as a straight line, right? The whole thing is going to be moving to the right. There's going to be acceleration this way. And if I assign the right direction as positive, it makes sense, right? Because then I'll get a positive answer. F equals ma. But now, I won't have that. Remember last time I had this little, the gravity acting on M1, or the smaller mass, slowing it down. In this case, the only thing that's pulling on it, the only thing that's actually causing motion is the gravity on M. Oh, that should be a 2. Give me a second here. All right, sorry. So then that's going to be F2. It's going to be pulling it down. And then when I can replace that with M2G, right? Because the force of gravity is mass times gravity. And then dividing both sides by M1 plus M2, I end up with a new term that slows things down. Instead of this, previously it was M2 minus M1. Now I just have, M1 minus M2. Now I just have M2. Right? That's the only thing that's actually causing it to move is M2. And the denominator M1 plus M2 is going to be the inertial amount, how much it's slowing down. So M1 really only acts in the denominator to slow it down. Right, then I can plug in my numbers. All right, this was M1 with M2 was 5. This was 3. So it slows it down to 6 meters, 6.13 meters per second squared, or rounding it to 2 sig digs as 6.1 meters per second squared. And turn this into a vector. It's in the downward direction for M2. For M1, we could say that the mass is moving to the right at the same acceleration, 6.1 meters per second squared. Okay, but now if we do the same problem, but instead there's going to be friction on the board. So now we're going to add this force of friction that's going to be pulling on the system to the left. It's going to be slowing down the system. Right? We said that the acceleration is going to be in this direction, so the velocity is going to end up also to the right. So then, let's say ugly vector sign. So then the force of friction is going to be opposing that, so it's going to be going to the left. So again, with a frame of reference right positive, we do the same thing, but instead we're going to have our friction vector here. And that will, when we plug it in, is going to be negative, because it's to the left, negative mu times the normal force, right? There's a normal force acting on here. And the magnitude of the normal force is going to be M1G. Right? That's going to be it's opposing the gravity pulling on it. But that's up and down, but we don't have to worry about that because we know the direction of it is, the directionality is stored in that negative because we're worrying about the friction, right? Friction, we say that force of friction is equal to mu Fn, but we don't worry about vector signs here because we know that the force of friction is opposing the direction, but the normal force is always at right angles to the surface. So then the directionality is a bit complicated. So we don't worry about directionality in that expression. So I just say that this is equal to mu m1g. I always do that. I always have this as first I write it, force is equal to mass times acceleration, Newton's second law, as a vector equation. Then I write down the vectors that make it up. And then I switch to a scalar equation where I use since it's all in one direction, it's a one-dimensional system, right? So it makes sense then to just use the pluses and the minuses to differentiate the directions, right? And that's how we set up these problems. They're complicated problems that have, up, down, left, and right, and all kinds of weird things. But we set it up to be a one-dimensional system, so I don't have to worry about it, right? Everything becomes a simple scalar equation here. And then I can solve my scalar equation for A. I'm going to factor out G from these terms, these two terms. So I'm going to left with M2, take away mu M1, and then divide both sides by M1 plus M2. And again, I have my slowing down term, but this term a little bit more complicated because there's a mu M1. But again, I can just plug in my numbers, and it's now 5.76 or just 5.8. So we went from 6.1, I think it was, meters per second squared, and now because of the friction acting on M1, we're even slower at 5.8 meters per second squared. All right? So these are pretty complicated systems that I can simplify by applying the right frame of reference, and then it just becomes a mathematical problem. Now, when you solve the homework problems or any of the problems in this whole unit, please show all your work in the same way, right? Write your Newton's second law, write down the forces, write it as a scalar equation, and then solve. So make sure you always do this. You can't just, please don't waste your time trying to memorize all these equations I derive. Okay, physics is not about memorizing. Physics is about understanding and coming up with these equations, right? If you try to memorize them all, you're going to make mistakes. If you can work your way through and understand where these terms come from, right? We can look at this equation and think about what do these things mean, right? They're not just random letters. I know that acceleration is going to be, some factor of g, right? I'm going to take my regular gravity, g, in meters per second squared, and I'm going to make it smaller by a certain amount. And the amount that it becomes smaller is inversely proportional to the total mass. Right? The bigger M1 is, the more I slow down the whole system. Right? If M1 was 0, then these terms would both be gone and would just be M2 divided by M2, which is just 1, and the acceleration would be just equal to g. Right? If there was no mass, it wouldn't make any difference. Right? But because I have an M1, it's going to slow down the system via friction here. So this is my friction term. And it's going to slow down the system inertially as well, right? Because heavier things take more force to push, or whatever, force. And in this case, the other slowing down was via friction of mu m1. That was the friction term. In the first example, m1 was pulling down with gravity, and there was no mu, and it was just m2 minus m1. Well, I think it was actually backwards, m1 minus m2, but you get the idea, right? So these terms actually mean something. That's the beautiful thing about physics, is even if we spend all this time figuring out this stuff, we can come up with these nice, pretty equations, there's meaning to them, right? There's meaning baked in. These things actually make sense. That's why I love physics, because it all makes sense. It might not make sense right away. Okay, so to keep that in mind, it might not make sense right away, but once we work through it and think about these things, it'll make sense. All right, so all I want you to do for homework here are these 5 questions. Again, each one, please work on them in the same way. Now, 23, though, is a little bit different. 23 is more of a conceptual problem. Okay, so we have two gymnasts. They both weigh exactly the same, and they're on a like a pulley. So they're both M1, M2, right? What happens if one of the gymnasts, starts to pull herself up on the rope with an acceleration of 1 meters a second squared? What happens to her, and what happens to the other gymnast? So what happens if one girl pulls on the string? How's that going to affect the whole system? Okay? All right. So that's it for today. This was lesson 2, and hope everything's going all right. Ask any questions if you have any problems, and take care. Bye.